Hello Brain Shakers, welcome to the Brain Shakers Academy. In today's session we are looking at the hemoglobin component. Now the hemoglobin component is an important aspect as it plays a key role in the transportation of oxygen in our systems. Now where is the hemoglobin component situated and where does it come from? So let's find out. So the hemoglobin component, which is an important component in the circulatory system, is found in a special type of cells that we call the red blood cells. So we have the red blood cells. Now these red blood cells are cells that are then produced by the long and flat bonds. So you have long and flat bonds, and these long and flat bonds are bonds such as the femur, the humerus, the sternum, and the ribs as well. They are responsible for the production of quite a number of cells. And the cells that are then produced are influenced to produce red blood cells by a hormone from the renal system or from the kidneys called erythropoietin, which then stimulates the process of erythropoiesis, which is the formation of these red blood cells. Now, within the red blood cells is a very important component which we call the hemoglobin component. Now, if we look at this hemoglobin component within the red blood cells, the hemoglobin component is comprised of three main factors. So we are going to say there is what we refer to as heme, and then there's what we refer to as iron, and then there is what we refer to as globin. So these are globin chains. And this is why oftentimes when they check your blood levels and they tell you that your iron levels are on the lower side, it is because the iron element in blood is in the hemoglobin molecule. When they tell you that your iron levels are within normal, it means that you have a hemoglobin molecule that then has the capacity to carry oxygen at adequate and optimum levels for your body. Now, these three are the main components that then form the hemoglobin molecule. Now, let's look at these components one by one and then see where they are coming from. We will start with the heme itself. So the heme itself is basically made out of a component that we refer to as a protoporphyrin ring. So how does it then come or become a protoporphyrin ring? So the heme is formed in the cytosol and in the mitochondria of the red blood cells. So the cytosol is just the fluid compartment of the red blood cell itself, and then the mitochondria is what you often refer to as a powerhouse. Okay, that's where most of your adenosine triphosphate or the energy is being generated from. So it is formed from these two. Now, how is it formed? There is condensation of what we call a glycine molecule and succinyl-CoA. So this is a coenzyme, okay? Coenzyme A. So once these two have then been condensed, they will form what we refer to as a protoporphyrin ring. Protoporphyrin ring. Okay, so they form a protoporphyrin ring, and when this protoporphyrin ring then comes to combine or bind to iron, when it does bind to iron, and this iron is the ferrous type of iron and not the ferric type of iron. We'll look at that when we look at the iron component. When it then binds to the ferrous, that's when it becomes the heme part of the hemoglobin molecule. Okay, now let's look at the iron itself, which is the second component of that hemoglobin molecule. So number two, we have iron. So the iron in the hemoglobin molecule is the ferrous type of iron. So the 2+ there, that is the ferrous type of the iron. And we know that iron is going to form about 6 bonds. Now, when it forms these 6 bonds, it has a component on it that will, 1, bind to the oxygen. Okay? One other component is then going to bind to an area on the alpha globin chain, okay, that we call position 87. Okay, so it is position 87 of the alpha globin chain itself, and then 4 of these bonds will be on the protoporphyrin ring. So the protoporphyrin ring has nitrogen end terminals, which are called the end terminals, which are 4 terminals, and that is where the ion is then going to then bind and make those 4 bonds. So it makes about 6 bonds. One of it will be to bind to the oxygen, and the other one to a histidine molecule on position 87. So this position 87 has what we call a proximal histidine molecule. Okay, it is at position number 87. Okay, now it has made those 6 bonds, and once it has made those 6 bonds, one of it is going to remain vacant because it has to bind to that oxygen. And this is why when your iron levels are very low, it means that oxygen now is not going to be transported, because the hemoglobin molecule's job is to transport the oxygen to the tissues for utilization, so that the cells will continue to respire and the cells will continue to function. But when your iron levels are very low, it means that there will be no iron levels to then bind to that oxygen, because they have a bond that they can create with the oxygen. Now, there is a position also on factor number 89, or position number 89. So we did make mention that the same ion is going to bind to a histidine molecule, which we are referring to as a proximal histidine molecule, around position 87 on the alpha chain. Then there is another position that we call position 89. So this position 89 is closer or adjacent to where the ion molecule forms a bond with oxygen. Now, this 89, or position 89, houses a special type of histidine molecule or histidine residue, which we call the distal. Okay, we call it the distal histidine residue or molecule. Now, what is the role of this distal histidine molecule? So it plays 2 key functions. Now, the 2 key functions are that this ion molecule has the capacity to bind to oxygen, and because it has the capacity to bind oxygen, it can still bind to carbon monoxide. So the role of this distal histidine residue is that if this ion molecule forms a bond with the carbon monoxide, it should be able to then be separated from the carbon monoxide. So it prevents the ion molecule from making an irreversible bond with carbon monoxide. That is the role of the histidine molecule. That is function number 1. The second function is that it is going to prevent the oxidization of the ferrous type of ion, meaning that we are not going to move from the ferrous type of ion to the ferric type of ion, where we have 3+ here. So this would be an oxidation process. So this distal histidine residue is going to now block this transformation, because once you have the oxidation of ion into the ferritin into the ferric state, then you end up having what we call metahemoglobin, which is then going to bind and not bind well to the oxygen. So you want a state of the ion that is going to bind to oxygen and be able to transport that oxygen to the tissues. So basically that is the role of that distal histidine residue that we find at position number 89 of the alpha chain of the globin molecules. Now let's look at the third component of the hemoglobin molecule, which is the globin chains themselves. Okay, so we have about 4 globin chains, and of those 4 globin chains, it means that we have globin chains, and these globin chains, we have alpha globin chains and we also have the beta globin chains. So we have 2 alpha globin chains and we have 2 beta globin chains. So with the hemoglobin molecule, you find globin chains like that. So these will represent the globin chains, and in between those globin chains, you are going to find more, I'll just put cycles in there to represent the heme molecule, and in the heme molecule or within that heme molecule, because it forms protoporphyrin rings, and so in between those protoporphyrin rings, you will definitely find ion elements there. So that will be your ion there, which is making a bond that is 4 bonds with the protoporphyrin ring and then makes a bond with the globin chains, and at the same time we will reserve another position to make a bond with oxygen. Now, the globin chains here, you have 2 alpha chains and you have 2 beta chains. Now, what happens and what is important to note is that with the alpha chains that you find, and you have the beta chains here. So with the alpha globin chains, you will find that they contain what we refer to as amino acids. So the alpha chains contains about 141 amino acids, and the beta chains will contain about 146 amino acids. And all the genes of the alpha chain or the alpha globin chain will be expressed on chromosome number 16, whilst those ones of the beta globin chain will be expressed on chromosome number 11. Now, these globin chains play a key role in also helping and facilitating the transfer of that oxygen molecule. And when the hemoglobin molecule is then being destroyed, or when the cell itself, like the red blood cell, has undergone a destruction, the globin molecules will then transfer to their smallest components, which are the amino acids. So they'll be broken down into amino acids and then will be stored into an amino acids pool and then later reused for further manufacturing of the globin chains. Now, what happens if the ion or the red blood cell has then been destroyed? What happens to the ion? The ion is then going to be reused or taken up by the body and later reused in the formation of further red blood cells. Then what happens to the heme itself? So the heme is then going to undergo a reduction. So when the heme has been broken down, the protoporphyrin rings have then been broken down, they will give a component that we refer to as bilirubin. Okay, so this bilirubin will then further be reduced. It will then further be reduced into what is unconjugated bilirubin. But before you even get to the state of bilirubin, the protoporphyrin rings will first be reduced into a component that we call biliverdin. So you will have biliverdin here, and the biliverdin will then be reduced into bilirubin. The bilirubin is what then is going to be in a form or state that we refer to as unconjugated bilirubin. And if it is unconjugated, it has to then transfer to the liver for the process of conjugation, where it is then going to bind to a component that we call albumin. That protein then transports it to the liver for the process of conjugation. And if it is not conjugated, then then there will be a higher amounts of unconjugated bilirubin that will be circulating in the system, and then you end up with a condition that we refer to as jaundice. I do look at jaundice in a separate video, and we'll look at the pathophysiology as well of jaundice, where we explain the whole process of bilirubin and the destruction of the red blood cells in a separate video. So do look out for that video as well on my YouTube channel, which is the Brain Shakers Academy. So basically that is the hemoglobin component, where you have the heme, you have the iron, and you have the globin chains as well. Very important structure in the transportation of oxygen. If you do find this particular video helpful in understanding the hemoglobin component, please do give it a thumbs up. Drop me comments in the comment section. I would like to hear what you think about. If you have any questions, please drop those questions in the comment section and we will respond to them. Thank you so much for watching, and as always from me, it's goodbye, and I'll see you in the next one.